right, let's take a look at our next section of this unit called solubility. Now, solubility, essentially, solutions make it easy to handle chemicals. It basically facilitates chemical reactions to occur, and we can control reactions a lot better when we have solutions. So solubility is essentially the property of a substance or a solute to dissolve in a solvent to form a solution. So essentially it's to what extent a certain entity will dissolve in a solvent. So we can have either a saturated solution where no more solute can be dissolved into a solvent, and we can have a supersaturated solution where more solute is dissolved in a solution than the solute can dissolve. So what happens is we often we can get more levels of solute dissolved into a solvent, generally when we increase the temperature. Now, that depends on what we're trying to dissolve, which we'll talk about in a minute, but in general, temperature affects the solubility of a substance. So we can have a supersaturated solution by either heating or cooling an entity or a solution to cause more solvent to be dissolved. Now, if we were to say heat the solution so we could add lots more sugar, then if we were to add sugar to water, we'd be creating like a syrup. Then what happens is as that syrup sort of cools, we may get some more crystals or something formed, or we might not get all of our sugar dissolved once it cools, but we can once it heats up. So we're going to talk a little bit about what solubility means and some properties of solubility. So we have some generalizations, to talk about when we talk about solubility of entities in water. So solids, when we talk about solids, we talk about how they generally have higher solubility at higher temperatures. So we're talking about things like sugars or ionic compounds. Generally, both molecular solids as well as ionic solids have a greater solubility at a higher temperature. So if you were to try and dissolve it in water, if you were to heat it up, you would dissolve more of that solute in the solvent. Gases are the opposite of that. Gases actually are more soluble at lower temperatures. And an example of this is if you were to get yourself a glass of cold water out of the faucet at your house, and it's nice and cold coming out of the tap, and then you let your glass of water sit on the counter for too long, and you'll notice that there's some small bubbles on the edge of your glass. Well, what happens is because at really cold temperature, there's lots of gases or air dissolved into that water, that when it warms up to room temperature, that gas can no longer be dissolved in the water. And it actually starts to form on the edge of your glass because it's not dissolved in the water anymore. It sort of bubbles out, which is kind of cool. We also see that we have higher solubility of gases at higher pressures. So if we increase the pressure, we can have more oxygen dissolved in, or any gas for that matter, dissolved in our water. Now, generally, we talk about oxygen because it is an entity that is necessary for life. Liquids. Liquids are kind of a tricky thing to generalize because we can have polar liquids and non-polar liquids. Now, polar liquids, they dissolve in water, and essentially if you have warmer water, polar liquids will dissolve better in warmer or hot water. Okay, we also have insoluble liquids that are non-polar. I think I gave an example in a previous lesson about trying to dissolve oil in water. Oil is non-polar and water is polar, so those two things won't dissolve. And some liquids will dissolve readily in water, or in other words, it essentially has no limit to what you can dissolve in the water. It's called being miscible. It can be dissolved to any sort of degree in water. Again, if I go back and talk about our solids, there are some solids that are insoluble in water, and we'll talk about that with our solubility table in a moment. Okay, now elements generally have a low solubility. So if you can imagine, if you were to put carbon, which is like a diamond, for example, in water, you're not going to get any dissolving there. Same with if you were to put a piece of iron or any sort of solid metal into water, you will have very low solubility. Okay, we do have halogens and oxygens that do dissolve in water to a small extent, but they're so reactive in tiny concentrations that they're very important in solution reactions. So oxygen and our halogens do sometimes dissolve in water, but they generally are pretty reactive and they'll form other compounds very quickly. Now, if we take a look at our solubility table, this is a picture of your solubility table right out of your data booklet. So maybe at this point you can open up your data booklet and take a look at this with me now. But what we see here is that we have a variety of solubilities for different ionic compounds. Now, the way to use this table in general, and the things that I like to add in, I like to start by adding in where it says the solubility is greater or equal to 0.1 moles per liter, or it's very soluble. I like to write beside this that when I record the state of matter for any of these compounds, it will be aqueous. They will dissolve in water. Now remember, when I have AQ in brackets, it means dissolved in water. If I was to have AL in brackets, it would be, dissolved in alcohol. Now, in this case, because these are talking about water, it is looking at specifically water, we're talking about aqueous. Now, when it talks about solubility less than 0.1 moles per liter, or it's slightly soluble, essentially these entities are going to form solids with water. So this is what I'm talking about our solid entities. Some of them are aqueous, some of them won't be. Now, when we take a look at our ions, essentially what we can do is, if we're looking at an ionic compound, we can look at the anion in that ionic compound to find the solubility on this table. So for example, if we have sodium chloride, we see chloride ions being right here, and that in order to figure out if sodium chloride is soluble, I go down my table. If it falls into this top column here, or this top row, I guess, I should say that it is an aqueous solution. Now, if I have copper chloride, silver chloride, mercury chloride, lead chloride, any of these entities down here will be a solid when mixed with chlorine, bromine, or iodine. Okay, so if I have a compound with this anion and this cation, it will be a solid. However, everything else will fall under this very soluble phase. So if I'm talking about sodium chloride, which is table salt, I do know that that one is for sure aqueous. It will fall in this column, and I would write it as an aqueous substance. Now, I said initially that there's all anions in this top portion of this table, but you will notice that we do have one cation, and it's our ammonium polyatomic ion that is in this table as well. But in general, if I was to generalize this, this is all anions. So again, some of these tables, we see that they are, it's a little bit different for different sections, but in this first section of our ions that we have, the solubility of only these entities are insoluble in water. So only rubidium chlorate, cesium chlorate, silver acetate, and mercury acetate, these are the four entities out of all of these compounds that can potentially be made with ammonium nitrate, chlorite, chlorate, and acetate. Essentially, only these four will be solids. The rest of every other element that can be mixed with one of these ions will be soluble. So, and that is also, we can't forget that we include our group 1 ions in there as well, which if we look at our periodic table, check out group 1, it's any ions present there will also follow this rule. Now, if we were to follow through with any of these examples, the same principle stands that if we have the ion up here, if we have an entity that falls in our top row, it means it's aqueous, bottom row will be a solid. So using our solubility table becomes very important when we have to predict and identify different chemical reactions. So when we talk about saturated solutions, we have the fact that most substances will only dissolve to a certain extent in a solvent. So if we talk about water as our universal solvent, we have, let's say, sugar. Well, sugar will only dissolve in water to an extent before I can no longer dissolve any more sugar in that water. And the reason that water is actually such a good solvent, it is our universal solvent, is a variety of reasons. Part of it is it's a polar entity with both a negative and a positive dipole in that polar substance. It is also a small molecule, which is very important, and it has a variety of intermolecular forces, which can also be important when we're talking about solvents. So, we have to look at kinetic molecular theory, which we've talked a little bit about when we talked about gases. We're talking about the vibration of particles or the movement of molecules. Okay? And we have a balance between what we call dissolving and crystallizing. So we have this process of dynamic equilibrium. So essentially what that means is if we have a supersaturated solution, now let me see if it's on here. Okay? If we have a supersaturated solution, which is a solution where you have so much, let's keep with our example with sugar and water. We have so much sugar in the bottom of our container that essentially if we picture this, let me draw these two out here. I'll draw two different beakers. Let's draw them on the side here. One beaker like this and another one like this. Okay, essentially if I have, actually, you know what, I only need one. I can demonstrate what I'm talking about with one beaker, I think. If I have a solid entity in the bottom, let's just go with that this is sugar, okay? I have sugar kind of down in this portion of my beaker here. And what's happened is I've dissolved as much sugar as I possibly can into this water. All right, now what's happening is that in the water, I have lots of sugar particles dissolved there. Okay, now sugar molecules are in there. And essentially is that some of these sugar molecules are forming crystals and they form this sugar sitting in the bottom. However, when that happens, there's this simultaneous concept where we have our sugar crystals that are being dissolved and are dissolving themselves into the liquid water. So we have an equilibrium, or what we call a dynamic equilibrium, between crystallizing to form a solid and dissolving to form our aqueous solution. So we have a dynamic equilibrium, which is a balance of two opposing processes that occur at the same rate. Or in this case, we have crystallization and dissolving. So a solubility equilibrium must contain dissolved solute and undissolved solute at the same time. So that is what we're talking about when we talk about a supersaturated solution with lots of crystals sitting at the bottom. Now, when we talk about solubility and ions and this concept of dynamic equilibrium or crystallizing and dissolving, we can look at an example. We can talk about calcium sulfate, which looks something like this, and this is a solid, and this would be this crystal form of calcium sulfate. So if we look at an ionic compound rather than sugar as our example, or fructose, okay, let's look at how this occurs. So essentially we have this reaction where we have calcium ions formed and sulfate ions formed. Now, the reason why we have these ions formed is when we do have dissolving, which is taking this crystal, dissolving it in water, we have dissociation of our ionic compounds. However, what happens is sometimes when we have a supersaturated solution, we will also have these ions present in our solution that react together. They hit each other or run into each other, like that kinetic molecular theory that we were talking about, that these two ions will bump into each other at the right speed, at the right force, the right angle, and we will create a calcium sulfate solid or a crystal. So we have this balance or dynamic equilibrium of our solubility and dissolving and crystallization. Now, again, as you go forward, I would definitely suggest taking a look at some practice questions, either from online or in your textbook prior to going on to your assignment. I would also be very, very certain and familiar with your solubility table and how to use it. So if you need to go back to that portion of the lesson and rewatch that section, I would definitely recommend that prior to completing your assignment. So, good luck!